All right, so good morning, everybody. I wanted to start with a brief recap because I gave these definitions right at the end, and I had a few people, come up to me and ask me about these definitions. They were sort of weirded a little bit. They were worded a little bit strangely. So, okay, so lecture 2. And recap. And even though I'm saying recap, I'm going to write things a little bit differently. So here K is, as always, a compact subset of Cn. And last time we defined the rationally convex hull and the polynomially convex hull of K. And today, rather than give those definitions again, it's actually easier to think about these things if you try to ask what does it mean for an element not to be in the rationally convex hull. That's kind of easier to understand and say. And in the same way, we'll sort of try to understand what does it mean for something to not be in the polynomially convex hull. So this happens if and only if you can find a holomorphic polynomial. So remember, this notation is for the class of all holomorphic polynomials on Cn such that, so P sub z just means that this depends on z. I'll switch between this and this for z, and I might also switch between z and z. I'm sorry about that. Okay, such that this polynomial vanishes at this point, and it does not vanish, is non-vanishing on K. So we will do examples, and we can also write something similar for a point to not belong to the polynomially convex hull. Here we need to be able to find a holomorphic polynomial such that when you take the absolute value of this polynomial evaluated at z, then this exceeds the norm of this function, the sup norm of this function on K. Okay? And so there is an immediate observation. So before we do a few examples, and then the main sort of topic of today's discussion is what does this have to do with approximations. So the immediate observation which you can deduce from this discussion here is that if z is not in the polynomially convex hull, then z is not in the rationally convex hull, which I'm just going to write this in many different ways. Oops, all of this just is to say that the rationally convex hull of a set belongs to the polynomially convex hull, and something we have already observed is that K is obviously contained in both these hulls. And then another implication is that if K is polynomially convex, then it is rationally convex. And of course, the converse is not going to be true. We are going to immediately see an example of that, but this is something that immediately follows from what we've written over here. All right. So before I state a few more properties, and I will leave a lot of exercises today as well, let's do some examples. So as is often the case with these kind of objects, things are very simple in dimension 1, but it's worth going over the argument. So n is equal to 1 over here. So and of course K is a compact. I mean, I'm not going to keep repeating this, but let's just put this down over here, so in C. So let z not be in K. Now choose Pz, let me take A, it's easier. So here's my polynomial in C. Clearly this vanishes at A, but it doesn't vanish anywhere else. So what this is telling me that nothing outside K is in the rational hull of K. Okay, so all compact sets of in the plane are rationally convex. All right. Now what about polynomial convexity? So I'm going to give you the answer, and then I'm going to give you some indication as to how you can prove this. So what we have to do, and this is sort of already observed yesterday, that the problem So this has something to do with approximations, polynomial approximations. And the problem with having polynomial approximability on K were all the holes that K has. Okay, so K union, and what I do is I take the union of all bounded components of the complement. So I look at the complement of K, and there will be lots of different connected, so when I say components, I mean connected components. So there will be all these connected components. One of them will be unbounded, which is what I asked you to think about yesterday. The rest, which are bounded components, we throw them in, and then this turns out to be the polynomially convex hull of K. Okay? So the fact, so here these are exercises. So this containment, that if you take something in a bounded component that is indeed in the hull, this goes via the maximum principle. And it's a repetition of an argument that we already saw yesterday. Okay, so you can try and complete this. How about this side? Okay, so if I want to show that everything in here lies over here, we sort of do it, we sort of do the contrapositive. We take an element in the unbounded component of, so this goes via, so if you want to complete this argument, you take an element in the unbounded component of C minus K. So that's some point. So let A be in the unbounded component of C minus K. Note that if I look at K union A, this has connected complement. Oh, sorry, let me see what I've done over here. No, this is not what I want to say. Yes, so what I want to say is this object, so this. So for now, let's just call this K prime, because we haven't yet shown that this is K hat. Okay, so I'm going to call this set K prime. I'm going to take a point in the unbounded component of C minus K, and when I throw it in, that has connected complement over here, and so then I can use Runge's theorem from yesterday, polynomial version, and what do I want to do? To construct PA satisfying double star. So let's call this star, and let's call this double star. Okay, so you kind of have all of the hints over here to complete this exercise. By the way, note that in characterizing polynomial convexity in one variable, I'm using this theorem and I haven't proved it. And I'm not sure, it depends on the time. It doesn't follow from what we are going to prove today, because what we are going to prove today, when you apply it to the one variable setting, you will need this characterization. So it doesn't follow from what we are going to do today. If we have time next time, I might talk about Runge's theorem. Any questions at this stage? Yes? To belong to the rationally convex, right. So remember, yes, because let's see why that is true, right? So you want to say that if Z is in K, then Z has to be in the rationally convex hull. That's what we want to say, right? So why is that true? Suppose I take a Z in K, let's go via this. So let Z be in K, okay? Is it possible to find a polynomial that vanishes at Z but is non-vanishing in K? No, right? Because it already has a 0 in K. So this cannot happen. So that means Z is always in the rational hull. Okay, does that make sense? So the other one is, this is in fact contained, so the rational hull is in fact contained in the hull, but if you want to see this directly, once again, what do you need? So if z is in k, then for any polynomial, let me write this argument here, for any polynomial here, if I take, what do I need to check? I take the absolute value. I need to check that this is at most the norm of p on k. But that's true because this is the supremum of all these values where z is coming from k. Both are always at least k, right? And that statement is over here. So this is an important statement. No, that's a good point. This is important. So whenever I might use the word non-trivial hull, and that means that there is something more than k. Okay, so in this case, the hull is always trivial in the sense that it coincides with the set. And here, if you have holes, then that's the non-trivial part of the hull. Okay? Any other questions? Yeah, these are like very fundamental objects in this course. So please, if the picture is not clear, you should ask me at this stage. And this is also an exercise worth thinking about. So please complete this. Maybe I might put a bit more in the notes when I post them. All right, so that's, so in dimension 1, we have a very clear understanding of rational and polynomial convexity and what it means to take these hulls. Things are not that easy in higher dimensions, but we should do at least, I should give you at least a large collection of examples. So let K in Cn be a convex compact set. And I already mentioned what convexity means. This is just classical convexity, that if you take any 2 points in this set, then the line segment connecting them is also in this set. Okay, that's what I mean by convexity. And I will use a non-trivial statement about convexity over here. And my claim is, so claim is that K is polynomially convex, and that implies that it's also rationally convex. Okay, so what I need to show is that if I take a point outside K, then I'm going to show that there is such a polynomial that satisfies double star. Okay, so let's prove this. And the proof should remind you a little bit of this thing we were doing yesterday in CR geometry, like going from real linear algebra to complex linear algebra. That's sort of pretty standard technique that you'll see in other parts of several complex variables. So let's say this is what K looks like. And I take A. So let, did I want to take A? Let me just take Z, doesn't matter. Okay? Let Z be not in K. Then, and this is the non-trivial statement that if you have taken a course in functional analysis, you may or may not have seen this version, but it's something that I'll post a note about this, and you can read about this theorem. So what the Hahn-Banach separation theorem tells us, in sort of in terms of pictures, it tells us that there is a real hyperplane, something like this, that passes through Z but does not intersect the convex set. Okay? And so this is a kind of separation property that I may have mentioned yesterday also. So, but what does it mean in terms of functions? There exists an R linear, a real linear function, small l, and I'm treating Cn as R to n to R, given by, so let's write down what this explicitly looks like. So I'm going to use these coordinates xj plus I yj. So this is given by summation aj xj plus bj yj, j from 1 to n for some aj's, bj's real, such that, so two things happen. When evaluated at this point, say you get the value 1 and L on K, the supremum, the norm of L on K is strictly less than 1. Okay, so this is the mathematical version of the picture that I have drawn over here. This is what we get, and you need to sort of take this on faith if you don't know what this separation theorem is. All right, but that doesn't, I mean, we're sort of there. This is sort of doing this. I mean, this is 1, and this is strictly less than 1, but this is a real linear function, it doesn't seem to be a holomorphic polynomial. So we need to cook up a holomorphic polynomial using this object. And the reason why I wanted to do this example is because this is a very common trick which is useful in other settings as well.
Maybe you have to add a constant to L, because Z might be the origin.
What did I do over here? I see. Okay, sure, let me do it at this stage over here, or should I just,
you could say without
I'll just push everything. So okay, thanks, good point. So not equal, let me write this in red so that you can think about this. Yeah, thanks. Yeah, so something that when we make definitions, it's a good idea to ask ourselves, what are the kind of transformations under which a certain definition is invariant? I didn't make a fuss about this. There's a little bit of that in the assignment. But think about what happens when you move things under affine transformations. So you can shift things around. Rigid motions are fine. Yeah, okay, good. So we still haven't constructed the correct polynomial. So how are we going to do that? Okay, and so for that we use the fact that, so I'm going to cook up, let capital LZ be summation AJ minus IBJ ZJ, J going from 1 to N, and while I've written this is for all Z in Cn. So it's globally defined, and I will define an entire function e to the LZ. Okay, so then check. This is quite quick. You can, that real part of LZ is actually this real linear function that we had constructed. Thus, if I look at the absolute value of g of z, that is the absolute value of e to the, so that's e to the Lz, that's e. And on the other hand, if I look at norm g of k, then that is e to the norm L of k, and that's strictly less than e, okay? And so what's happening over here is that now we have cooked up an entire function. So it's, what is worth noting is that g is an entire function. And I erased double star, but that's okay. So the value of this, the absolute value of this function is strictly larger than the norm of this function on k. We wanted to cook up a polynomial that does that. This doesn't look like a polynomial, and so this is your exercise. Argue using power series that you can do this using some p over here. So what I'm using is that if you take any entire function, you have a power series expansion, then in the sup norm on k, you can truncate this power series and get polynomials that approximate that. So this is the correct object, but if I just truncate its power series at the right stage, I would still maintain something like this. I really just want that the value of the polynomial here, an absolute value, is strictly larger than the sup norm. Okay, so this is an argument that you need to complete, but the bulk of the argument is over here. Questions?
The first inequality should also be called that polynomial also. Both we need.
Yes, so your polynomial, yeah, exactly, both you need. So you need to make sure that you're doing the approximation on the correct set. Okay, but remember that you have a power series expansion on the full, on Cn, and that converges uniformly on compacts. So yes, so you have to be careful about where you do that approximation. But the good thing is that our polynomial is allowed to depend on this point z. That's the main thing. Any other questions at this stage? Okay, and so, so far what we have seen, we have completely understood this situation, and polynomial convexity is equivalent to the complement being connected. This example, I have something polynomially convex. Here also the complement seems to be connected. So I just want to warn you that in general, this is somewhat more delicate. So let's quickly talk about one more example, and then we will talk about approximations. So 3 Cn minus k is connected does not in general imply that k is polynomially convex. Okay? The converse is actually true, and this is an assignment problem. Maybe it was there in your, I don't know which one, but this is true actually. So if k is polynomially convex, then the complement is connected. In fact, one can say more about the topology of the complement, but we will not be going into that in this course. Okay, so example. So here I just need to give you an example. So what you do is you take k to be z1, z2 in C2, and I'm really actually just taking a planar example, and I'm just adding a dimension over there. So absolute z1 is 1 and z2 is 0. So it's in the z1 plane, it's the circle in the z1 plane. By adding this extra dimension, the complement is now connected, but we know the problem with this. What is the problem? What is something that's definitely going to be in the hull over here? Give me something, give me one point which is in the hull of k but not in k. So picture, okay, picture. This is z1, this is z2, and this is your k over here, just this circle over here. The origin. So that's, again, a maximum principal argument. So k is not polynomially convex. Okay? And if you want as an exercise, you can compute the hull of this object over here. So this, there is no complete characterization for polynomial convexity just via the topology of the complement. There's no topological description of polynomial convexity. Okay, let me see if there's anything else I wanted to say at this stage. So I wanted to mention a couple of properties which may or may not be useful, but I'll leave them as exercises. They're not that hard to prove. And this is something you may have already observed while we were doing these examples. One, k hat, and so both the hulls are always compact sets. Okay, so this follows from the definition. Please check. And the rationally convex hull, and this is also true of the polynomially convex hull, is the smallest rationally convex, and in the case of the polynomial hull, polynomially convex set containing k. So a few things are being said over here. Let's just stick to one of them. Let's take this. The one statement is that once you construct the rational hull, this is true typically when you have hulls in convexity, once you take the hull, then the hull does have the desired convexity property. So if I take the hull of this, I'm not going to get anything new. So this statement is saying that Rk is rationally convex, and if you take any rationally convex set containing k, that must contain the hull, the rational hull of k. Okay, that's what this statement is saying over here. So please check these two things using the definition. And finally, relationship with approximations, which is the title of this course. Okay, so why, and what I'll do is, I'm going to stick to the polynomial case, but whatever I'm saying, works in the rational case as well. The proofs will have to differ a little bit, but I'm going to just deal with the polynomial case. It's always a little bit easier to think about. So what we have is, let's assume that K is polynomially convex. So this is sufficient to get a Runge type approximation. I think this is the way to write it here. Okay, so this is a Runge type approximation. This appeared in Raphael's talk yesterday in a more general setting. So he was doing this in the setting of Stein manifolds. For us, our Stein manifold is Cn, but it's exactly the same statement that he presented yesterday. So if you have polynomial convexity, you have polynomial approximability of holomorphic functions. The converse is not true. We have already seen an example yesterday. We took the unit by disk and we subtracted a smaller by disk. You do have this feature, but that's not polynomially convex. Okay, so you do not have the converse in general. But I would like to point out something. I was hoping to prove it, but I don't think I'll have enough time. There is one kind of approximation that does imply polynomial convexity. So if you have this very strong statement, so somehow you happen to know that all continuous, complex valued continuous functions are polynomially approximable, then that does imply polynomial convexity. And there are situations in which that is actually useful. But I mean, there's a catch over here. There's a limited class in which this is useful. What is a necessary condition for this to take place? So remember that if you have a sequence of holomorphic functions on an open set and it converges uniformly on compacts, then what can you say about the limit function? It has to be holomorphic, right? So as soon as this guy has an interior, when you take uniform limits of polynomials on the interior, the function will be forced to be holomorphic. And of course, there are lots of continuous functions that are not going to be holomorphic on the interior of the set. So a necessary condition over here is that the interior of K is empty. Okay, so if you're trying to check for polynomial convexity and the interior is non-empty, don't even bother trying to do this. But if the interior is empty, then, I mean, maybe don't bother even then, because this is quite hard. But sometimes the stone Weierstrass or something can be used, which is a statement of this kind. The stone Weierstrass can sometimes be used in a useful way over here. Okay? All right, so our goal today is to sketch a proof of Oka-Weil. It's a little bit involved, so I'll try to give you the main idea. And I want to say something about how I'm going about proving it. Question, yes? Well, this is a closed subspace. So if this is true, then the closure of that is in there as well. I mean, the reason I'm writing it like this, because verbally I often say that holomorphic functions are approximable by polynomials. If I say OK closure is in PK, then that's like functions that are approximable by, I mean, this is the statement I've been saying verbally aloud. So I'll write it like this, but it implies what you're saying. It's equivalent to what you're saying, in fact. Okay? All right, so remarks about how we are going to go about doing this. Yes, okay. On the proof of Oka-Weil. So if I sort of just want to, if I don't care about anything and I just want a proof, then one can use a very big hammer, which was mentioned yesterday in the SCV overview, which is Hermander's L2 theory for solvability of dbar. Okay? And that gives me quite, once I assume this amount of machinery, then it gives me quite a concise proof. I'm not going to do this, A1. But I will mention something because I was asked this question yesterday in some context. So when you're doing this, I mean, what this allows you to do, it allows you to construct holomorphic functions which have certain desirable properties. And usually, I mean, that's this piece, but the L2 theory part also gives you estimates. But the thing is, they're usually estimates in the L2 norm, and I made a big fuss about, oh, well, we are doing approximation in the uniform norm. But you may have seen a very basic exercise in complex analysis where if you have some sort of L2 convergence, then you can try to deduce uniform convergence. So this requires, this transition requires something. So if you later get a chance to look at this proof, this is there in one of the references, I'll mention which later. This step of going from L2 to uniform, there is something involved in that, but it is possible. And the second piece, so this is one, and so we'll use a couple of small hammers. So I will not prove this, but these were also mentioned, and I think these have been repeated so many times by now that maybe you have started believing them. One is, if I take, so each holomorphic function, so this is holomorphic in a neighborhood of the closed polydisk, admits a power series expansion that is uniformly convergent on compact subsets of this. The domain of this is some open set containing this. So it's uniformly convergent on compact subsets of that, but in particular, it is uniformly convergent on this compact subset. So I have, what this means is that this guy does have, can be approximated by polynomials on the closure of the polydisk by truncating these power series. And the second piece is a baby version, but it's not, you really don't need L2 estimates of any kind. This is solvability, so I'll write this, so let U be a neighborhood of the enclosure, and so okay, sorry about this, but you sort of saw these PQ forms, so it's okay. So if this is a piece that you do not understand, that's totally fine. You can still follow the idea of the proof, but I'm taking a dbar closed PQ form on U, whatever that means. Then there exists a neighborhood W contained inside U of the enclosure and a PQ minus 1 form on W such that d bar alpha is equal to beta. Okay, so you have solvability of the system of partial differential equations. The data satisfies a certain compatibility condition. We've seen various versions of this yesterday, and in this setup, you can do this, and the reason why I'm calling this a small hammer compared to this is because you don't need any of the functional analysis over here. This can be done very concretely. You can actually write down a solution operator, and I mean, this is fairly concrete, but we will assume this. We will not prove this. Okay, any questions before we proceed? Okay. So let me start with the definition. So we are now going to go ahead and do the various steps of the Oka-Weil theorem. And there's a nice picture over here. So a set pi in Cn is said to be a polynomial polyhedron if there exists a finite number of polynomials, holomorphic polynomials on Cn. I was told to refill. It's getting lighter, right? The pen or something? Is it getting lighter? I don't know. Oh, maybe I'll just swap. Okay. So yes, so k is some finite number such that pi is carved out of these polynomials. So how is it carved out of these polynomials? You only consider those z's in Cn where all of these in absolute value are less than or equal to 1. So this is for all j from 1 to k. So it's carved out by k inequalities, where k is some finite number, finite positive integer, and so for example, standard example is the closed polydisk, right? I mean, after all, this is how it's, these are all polynomials, right? So the terminology is fairly obvious because if you took real linear functions, you know, a standard convex polyhedron is cut out by finitely many inequalities of this kind, where you replace these by actually real linear functions. So the terminology is not at all surprising. I should point out that the topology of these objects can be much more complicated than convex polyhedra. This may not even be connected. It may have many components. So don't be misled. Okay, so what do we do with something like this? So lemma. So somehow the polynomially convex set has something to do with polynomial polyhedra. What does it have to do with polynomial polyhedra? So I'm going to do another without loss of generality, and you have to think about this. We will assume, so what are we trying to prove? Okay, so we are trying to prove the following. So sorry for this badly written. So we are trying to prove Oka-Weil, this version, that if k is equal to k hat, then O of k is in P of k. Okay, so I have this underlying compact set, and without loss of generality, I'm going to assume that it is always contained inside the open unit polydisk. And you can sort of think about why this can be assumed. Okay, so lemma 1. Let U be an open set in Dn containing k. Okay, so let's draw a picture. I have Dn here. This is some sort of a schematic, and then I have some k over here, and then I have some open set U containing k. And what I'm going to do is I'm going to squeeze between k and u. So let me say something about, you know, why these are kind of nice objects. Okay, so this example over here, I've not just written this to give you an example. It's also kind of a model. Okay, so there's a lot of times analysis that you can do on this, you can transfer quite easily to these guys over here, and we'll see precisely how. Okay, so what I'm going to do is between k and u, I'm going to squeeze some sort of a polynomial polyhedron. I mean, I'm going to squeeze a polynomial polyhedron between k and u. Okay, so what's the statement? Let u be an open set in Dn containing k, then there exists poly pi contained in u such that, or maybe let me just say it this way, such that k is contained in pi is contained in u. By the way, by our definition, pi is a closed set. And this we can prove. Okay, so how are we going to go about it? So I'm going to take a point. So let Z be in Dn closure minus u. Okay, this is, by the way, this is a compact set. I'm removing an open set from this guy over here. Since k is, okay, so maybe let me write it like this. Since Z is not in the hull of k. So remember, k is polynomially convex. If I take any point outside of k, it's not going to be in the hull. And what does that mean by our definition? There exists a polynomial Cn such that if I look at this, I can take the absolute value of this to be 1, and I can take its norm on k to be less than 1. So I find such a polynomial, but polynomials are continuous, so I have found a polynomial that exceeds 1 over here and norm is less than 1 over here, but there's going to be some open neighborhood where I'm going to get an estimate, right? So let nz be an open neighborhood of z such that p of z is greater than, so I guess what I want to do is I want to create a gap over here. So by scaling, I can assume this. So I want to create a little bit of a gap. Equality I don't want to keep. Let's keep it like this. And so what I have is pz continues to be greater than 1 on nz. And that I can get by continuity. So I have found this function that works for this little neighborhood over here. This set is compact over here, so I'm going to cover it with finitely many balls. So this is compact. And so I can cover this region with finitely many balls that of this kind. Please interrupt me if there are any questions. So since is compact, there exists k polynomials such that if I set pi to be equal to, and what I'll do is I want to make sure that this object actually lies inside the polydisk. I'll throw in some more, I'll throw these in, and I'll throw these in. Such that if I set pi to be equal to this polynomial polyhedron, then a couple of things happen. The way I chose this, so what did I do at each, so I covered this region with finitely many balls, and what's happening on each of these balls is that at least one of these polynomial polyhedra are exceeding the value 1. Okay, so what that tells me, it tells me two things. So I'll write the second thing first. So if I take any point outside, so if I take this region, that's, how should I write this? Then z is not in pi, okay? So anything which is not in U, in fact, I can write it like this. Let me write it like this. If z is not in U, then it is not in pi. So why is that? If it's not in U, either it's not in the polydisk, in which case it violates one of these, or if it is in the polydisk, then there's going to be at least one polynomial where this inequality is going to be violated, so it's not going to land up over here. Okay, so this is just another way of saying that pi is in U. And on the other hand, all of these inequalities are satisfied on k, because look at the way we chose this polynomial. And that's how we are choosing all our polynomials. And so k is in fact inside pi over here. And that finishes the proof of this lemma. Okay, so let me just sort of briefly recall what we've done over here. We've not done much right now. I mean, where are all the approximations? Doesn't seem like there are any approximations right now. We're just trying to set up the correct structure. I mean, this is a very common technique where rather than work with the object itself, you kind of try to work with something simpler. And really, the simplest object over here is this guy, and we're going to try and reduce everything to this guy, okay? What this argument tells you over here, if you think about this, this argument really tells you that any polynomially convex set can be written as an intersection of polynomial polyhedra, okay? So that's another sort of exercise you can go, not finitely, I mean, you can just take the intersection over all class of polynomial polyhedra that contain the set. But let's forget about that and let's just come back to our picture. So I leave the lemma over there and let's sort of see how we can exploit this. And I have 10 minutes. Yeah. So let me draw for you a picture to explain what we are going to do. So let's finally come to the part. So pi over here is going to be like this. This is now fixed. K is fixed. Okay, K is fixed. Where is the u coming from? Remember, this pi was chosen dependent on u. So I sort of lied to you. Let K be given, and now let F be holomorphic on K. That's the guy we are trying to approximate. Now, what does this mean? Then there exists an open neighborhood u of K such that u is contained in Dn and F is actually holomorphic on u. That's what it means for F to be holomorphic on a compact set. So that's the u over here. Okay, so I have already fixed an F, I have found a u, and now using this lemma, I have found a pi. Okay, so this is the pi that we are going to use corresponding to this u. Okay, so how am I want to find polynomial approximations, and I'm going to show you a picture of what we are going to do. And this is a schematic, so you have to allow for a lot of inaccuracies and the fact that we don't have enough dimensions and I cannot draw straight lines. Okay, okay, let's try this again. So, and I'll sort of use real coordinates because they're just easy for the moment to think about, and so just kind of try to understand the picture more than anything else. So what we are going to do is we have this region over here, and let's take something that mimics, this is like my polydisk. Let's say this is D2. Okay, and it's sitting as some sort of slice in D3. Let's think of it this way. Okay, this is the picture. So the story is taking place over here, down in this slice, and I do have one more color over here. And forget about the set K. What you have is some sort of polyhedron, which I'm going to take a rather simple one. Okay, so I'm going to take a region like this, and we can even write down some equations over here. So let's say this is pi, and for the moment it's something like, and that equation over there, it's actually less than or equal to 3 over 2, but we kind of want to write everything as less than or equal to 1. And of course, forget about, like, you can think of this as unbounded. I'm not writing down these inequalities. Okay. So the advantage of allowing ourselves some more space over here, so technically this is defined by, these are just coming from the fact that this is sitting inside the byte disk, but this is really just one additional inequality, so I need one additional direction. And the point is that this guy over here is really the projection of some sort of slice of this polydisk up there. What is this slice? So if I look at D3 closure intersected with the following hyperplane, z is equal to 2 over 3 x plus y. Okay, and let's try to draw that. I don't think we have any more colors. I'll just use black maybe. So what does this slice give you over here? So you kind of get this, then on the top face it goes like this, on the back face it goes like this, and it goes like this. So this black guy up here, this is a slice of the polydisk in 3 dimensions. It's a sort of plane slice, and the portion that slice when projected down is giving you the polynomial polyhedron that you had in the first place. And what we are going to do, and this is sort of the, let me write down the statement, this is the key fact. So this is lemma 2, but I guess it's really a theorem, and this is known as the Oka extension theorem. Okay, so how do I want to say this correctly? I may not have even set up all the objects. Okay. So given f which is holomorphic in pi. So remember f is in fact holomorphic in U. U contains this compact set pi. So f is really a holomorphic function in pi. There exists, so what is happening is you have something which is holomorphic in some neighborhood of pi. Okay, so f is holomorphic in some neighborhood of pi. You can trivially extend it in this direction. So just do not make it depend on any of the variables in this direction. You can trivially extend it in a tube like this. But there is a portion of the polydisk over here which may not be contained in this tube. Okay, so there exists something which is actually holomorphic on, so we have how many? We have k extra terms. So I'm going to add k dimensions such that when I restrict f to this slice, so what does it mean to restrict f to this slice? I have n variables and then I have p1 of z to pk of z. So that is going to represent this slice over here. On this slice, it just becomes the original function. Okay, so I have something which I have trivially extended on this tube, and it's called an extension theorem because this guy is actually extending to a holomorphic function on an open set containing the red part. Okay, this is a very non-trivial statement, but it's also a very fundamental kind of statement in several complex variables where you have something which is not, I mean, a priori it's even on a lower dimensional set. I mean, this holomorphic function is living on a lower dimensional set and you are being able to extend it to quite a large set over here. And this uses the second small hammer that I mentioned, which is solvability of dbar on polydisks. Okay, so we are not going to go into the proof of this. Let me just pause for a second before I complete the proof of Oka-Weil and make sure that people are sort of understanding what's happening. Very quick recap. We had a compact set which we assumed lives in the polydisk down here. We have some region of holomorphicity of our function. In that, we have squeezed in a polynomial polyhedron. So this function is now holomorphic on a neighborhood of the polynomial polyhedron. What is great about polynomial polyhedra? That they can be viewed as slices of some higher dimensional polydisk. So that's the advantage. They are just projections of some slices. So the holomorphic function now lives on this slice, and some machinery allows us to extend this holomorphic function to a holomorphic function in the neighborhood of this polydisk. Okay? So that's what we've done. We've taken this f, extended it, and this is what it looks like. And let me write correct statements for all z. So this point lies inside pi. That's where it lies. Okay, that's the important part. Okay, let's finish the theorem. Now we are almost done. So final, oh, I should not have erased the picture. Oh, no, we do have a picture there. Okay, so final step. So by small hammer A, remember we have capital F is now holomorphic in a neighborhood of a closed polydisk. We have power series expansions. So there exists sequence of holomorphic polynomials in Cn plus k such that what's happening over here, capital Pn converges uniformly to capital F on Dn plus k closure. So we approximate this guy, capital F. Thus, now this approximation you can just restrict to this slice, right? So thus Pn Z1 to Zn, what does it mean to restrict to that slice? It just means I'm doing this. That converges uniformly to F restricted to that slice. For on these are now functions on pi, but these are now polynomials in Cn, because these are polynomials and you're composing them with polynomials, so everything is a polynomial, and this guy is just f. And so you have found, by sort of going into a higher dimensional space, you have found your polynomial approximations. And of course, if you sort of, ever care about the degree, you can see that the degree is coming from how well you can squeeze this. Not just the degree, I guess no. There's more information over here, but this dimension is coming from how you can squeeze this object between k and u. So this is, I left out a lot of details, but that is sort of the vague picture over here. I will not do the stronger statement, the continuous approximation, the approximation of continuous functions by holomorphic polynomials. That implies polynomial convexity. I don't think I'll have time to do it. I might put it in an assignment or something, but I think I'll stop over here.